I'm going to start out with some stories here some of you may have heard of. There was this machine back in the 80s that was dual purpose. It could do radiation therapy or x-rays, and the difference was that a plate would come down for the x-rays and not for the radiation. And there was actually a bunch of accidental overdoses where the plate didn't come down when it was supposed to, and people who were supposed to get x-rays got radiation instead. In '96, there was a really expensive rocket explosion where a $500 million rocket exploded 40 seconds after liftoff. And this one is personal. I was there in 2003, New York City, and the entire Northeast experienced a tremendously expensive blackout. And why am I telling you these stories? They're all caused by software bugs, okay? So there was, just the radiation machine was just very poorly tested, the code written by one person, and it had, a logic bug, and if you hit a certain sequence of keys on the control operation, then it had this mistake. The rocket explosion was an unsafe conversion from floating point to integer, and the software and the blackout is because there was an alarm system in Ohio, and the alarm system was actually producing messages, but it overloaded the message system and kept rebooting, and none of that actually showed up on the monitors where people were trying to monitor it, and by the time they did find out, it was too late. So, what can we do about things like this? So my area of research is formal methods, formal verification, and this is something that for a long time we've sort of said, hey, this might be a solution to these kinds of problems. Bill Gates, among others, called it the holy grail of computer science. And the idea is, instead of just testing your software, you actually do a mathematical proof that the software behaves the way it's supposed to. So this, as you can imagine, might be quite difficult, but in some cases, it definitely pays off. So let me just tell you more specifically what formal verification is. So there's three main steps. The first step is you create a mathematical model of the system. Now this sounds hard, but actually software artifacts are already mathematical objects because there's a well-understood semantics. There's not usually any ambiguity. You either have a line of code or you don't. So unlike things like physical systems where you do have to create separate models, software systems, you sort of get that for free. Now the second part is you have to specify what is the properties that this system should have. And depending on what you're verifying, this may be very simple or it may be very hard, right? So it could be that, you have it could be you have a piece of software that's trying to compute the fast Fourier transform, and there's a mathematical equation that says what it's supposed to do, and you can just check it, right? Or it could be that you have a machine learning system that's trying to identify a cat, and now the specification is, what is a cat? And that's extremely difficult. We don't know how to specify that. So this step could be hard or it could be easy, it depends on the system. And then finally, once you have a mathematical model of the system, once you have a formal specification, then you do the proof. Now, this sounds like it might be hard, and generally this is the hard part. But the good news is there's been a lot of advances in automated reasoning techniques. So things that used to be hard are now much, much easier. So we can do things like take an entire microprocessor and say, this microprocessor had better follow its ISA, and we can actually prove that automatically using automated reasoning techniques, whereas there's no hope to do it using exhaustive testing. So that's good, and I work in this area of automated reasoning, and these things keep getting better. But of course, the problems get harder too, because now we've got this whole new set of AI systems, right? And so what are you going to do if someone wants to use an AI system in, say, a safety critical situation? Can we use something like formal methods to help out? So that's one of the challenges that we're working on, and I'll tell you about some of this work. So to motivate it, I'm going to give you a case study that we did. One of my colleagues is working on this system called ACAS, which is the Aircraft Collision Avoidance System. This is Michael Kokendorfer in AeroAstro, and he actually is the author of the new international standard that's going to be on every commercial aircraft in the world for collision avoidance. It's basically a little box, and it tells you to go left or right or up and down if you get too close to another aircraft. And there's a whole bunch of really cool science behind how that all works. ACAS XU is a new system they're developing for drones. So this is aircraft that are unmanned. And the idea is each drone would have a little ACAS system that could interact with its autopilot or with the ground-based pilot or something, and tell it if there's some other drone in the vicinity that they need to watch out for. Okay, so basically the way it works is these little ACAS boxes get a few inputs from the environment. They know something like the angle, their own velocity, the velocity of intruder, the time until nearest approach with the intruder, and things like that. So you get I think 7 different inputs. And then your job is to produce an advisory. So the advisories can be turn strong left, turn strong right, turn right, or clear of conflict, which means you can just continue on your way. And of course, the goal is to, as much as possible, produce a clear of conflict advisory, because you don't want to give false alerts, but whenever necessary, to give the alerts that you need. Now, for various reasons that have nothing to do with verification, there were some compelling reasons to try using a neural network to solve this problem. The main reason is because on these drones, memory is a premium, and the current best technique involves a very large lookup table with gigabytes of space. And what Professor Kokendorfer showed is that you could actually use 45 neural networks and get a 1,000 times reduction in the space, and you actually got better performance in simulation. So that seems like a win-win. But, you know, do we really want to put a neural network on a flying thing? How do we know it's really going to do the right thing, right? Okay, so how can we actually verify that this system does what it's supposed to? Okay, so we know that neural networks generalize the set of training data that they're given. And we can certainly test the training data. We can test a lot of other points. But how do we know that there's not some point there that we didn't test where it does something drastically different and could cause a problem? So what are the kinds of things we might want to prove? We might want to prove that if an intruder is sufficiently distant, the advisory is always clear of conflict. If the intruder is in a certain space on the left, the advisory is always strong right, and so on. So I'm not going to talk about how we get the properties to prove. So there's a whole interesting research stream about how we come up with properties. But now I'm going to assume that someone gives us this network and a property to prove, and how do we actually check it? And I hope you can see that if we can do this, this can actually provide a crucial way for providing greater confidence about these kinds of systems. All right, so you probably are all familiar with this, but just quickly to review what a deep neural network is, you have some inputs, and then the inputs are passed through several layers. Could be fully connected, not fully connected, and then there's essentially these transformations that occur as it passes through each layer, and then finally at the end you get some output. In our case, the inputs are the sensor data from the ACAS box, and the outputs are a score for each possible advisory. So there's 5 possible advisories. You get a score for each one. The one with the greatest score is the action that you take. All right. So yeah, for these networks, we had 8 layers, 310 nodes, and there's 45 of them. Again, the details of why that's true is not super important. And before we started working on this, the state of the art, if you just took sort of an off-the-shelf tool to try to solve this, you could only handle about 20 nodes. It's pretty bad, even with, like I said, all these advances in automated reasoning. So why is that the case? Well, first of all, we showed this as an NP-complete problem, which is not too surprising. The expressive power of a deep neural network is very good. But then the real problem is most of the neural network is just a bunch of multiplies and adds, and we actually have pretty good techniques for reasoning about that. What we don't have a good technique for reasoning about are these activation functions. They're nonlinear, right? So you can't immediately represent it with these sort of convex optimization techniques. And the problem is, so basically they're very simple, but they're sort of the simplest possible nonlinear thing. And the sort of existing techniques that we had couldn't do anything very smart with this. So what would happen is you'd have to say, okay, well, let's just consider the case where this activation function is in its linear region, and there's two cases for every activation function. If you do that, it reduces to a linear program, which we know how to solve. However, if you do that, you get 2 to the 300 cases, even for this small network. So that's not really a feasible solution. So what I'm going to show you is an algorithm that we came up with to solve this. And the basic idea is we're going to take an existing linear programming algorithm, and we're going to insert into the guts of the algorithm some intelligence about these activation functions. So it's really the idea, and this goes back to sort of a philosophy I have in my work, is rather than trying to take an existing solution, an existing solver, automated reasoning tool, and make it work with a new domain, let's actually modify the solver. And there are a lot of, there's been some work that makes this easier to do. Okay, so that's what we're going to do. We're going to go actually change the tool that we're using and modify it to match the domain. And I think this is actually an exciting area in automated reasoning, is doing this more domain-specific reasoning. All right, so how does this work? I'll show you with an example. Okay, so we're going to look at a very, very simple example where we have one input, one output, and one hidden layer with 2 nodes. And I'm going to show you how we encode this problem and how we solve it. All right, so what we're going to check, someone gave us this property. It just says, hey, I want x1 to be in the range from 0 to 1, and I want the output x4 to be in the range from 1/2 to 1. Is that possible, right? So if it is possible, I'll give you a solution. If it's not possible, I'll give you a proof that it's not possible. That's the kind of tool that we're looking for. So first what we can do actually is for each of the edges in the network, we can represent that edge with a simple linear equation, okay? Now notice though, what we have to do is we split these activation functions into 2 nodes. And this is key because we're going to actually model the input to the activation function separately from the output. All right, but then for the input, say this x2w, I don't know if you can see this now. For this x2w, it's just going to be equal to x1, right? So that first equation just says that x2w is equal to x1. And the next 2 equations just model the other edges. All right, that's pretty straightforward. Then what we're going to do is set up some bounds. Okay, so every variable has an upper and a lower bound. The input and output bounds are determined by the property we're trying to check. And the internal bounds are unbounded, except the output from a ReLU activation function is always non-negative, so that we have a lower bound there. Now, the tricky thing, the new thing is we're going to add these special constraints, right? The special constraint says that x2a had better be equal to the ReLU of x2w. All right, so this is new. We've added this, and this becomes part of our problem. All right, so now I'm going to show you just a really quick step through of how the algorithm works, so you'll see how these special constraints get integrated. So first, and this is applying, if you're familiar with linear programming, the simplex algorithm. This is using the simplex algorithm, but I'll walk you through it if you're not familiar. It's pretty straightforward. Basically, we have this sort of table. For every variable, it has an upper and a lower bound, and it has a current value, this assignment value. And our goal is to get the values of every variable between the upper and lower bounds, right? Sounds easy. Okay, and we also have to respect the equations. So you have to make sure the equations stay true, and every variable is between its upper and lower bound. So we start with something like all zeros. All zeros makes all the equations true, so they're happy. But then, of course, you can look very quickly and see that x4, the value of 0, is not between 1/2 and 1. So we have to do something. So what we're going to do is we're going to update x4. Now, in this case, we can just add 0.5 to x4, and then update any equations that depend on x4. So that's what we'll do. We'll add 0.5. We update x4. You can see that it also affects x7. So we're going to update x7. Great. Well, we fixed x4, but now we have a problem with x7. So this is the way this algorithm works. Now x7 is on the left-hand side of the equation, so now we have to do what's called a pivot operation. So we're going to pivot x7 so that it's not on the left-hand side. We're going to switch it with some other variable that's on the right-hand side, in this case x2a. Now we can update x7, which is great. We'll also have to update x2a. And now here's where we actually do something different. We have this little connector that connects x2a to x2w, and we say, oh, because I updated x2a, I better also update x2w and make sure that I keep that ReLU constraint satisfied. All right, so that's sort of what's new here. All right, so now I can continue. You can see that, let's see, I still have a problem with x5 here. So I'm going to fix x5, and that's going to affect x1 and x6. So let's fix that. And I think we're almost there. Yeah, we got to fix x6. And success. Great. Okay, so if you look, you can see that all the variables satisfy the equations. The values are within their bounds, and most importantly, the ReLU constraints are also satisfied. Now notice we didn't have to do any reasoning by cases here. All we did is we kept track of when we made a change to a ReLU output, we also made the change to the ReLU input. Okay. Let me just say one more word. Now it doesn't always work, right? So you can't get a sound, complete terminating algorithm just by making these steps. But in practice, what we do is we do this sort of greedy approach, and then if we see that there's a particular ReLU pair that keeps getting broken, we keep having to fix it, then we'll do an actual case split on that. And what we found is that in practice, we only had to do that case analysis about 10% of the time. So we took our case analysis tree from 2 to the 300 to 2 to the 30, which is actually tractable. So I'll show you some examples of what we were able to show. So I won't go into the bitter details, but essentially there were properties that look like this. If the intruder is near, approaching from the left, then the network should advise strong right, and then this breaks down into very specific ranges on all of the inputs. So we set all those ranges on the inputs, and we say that the output should be a specific thing. And we're able to prove this for the networks. All the networks satisfied this property. Then another property that we were looking at is something about if the vertical separation is large and the previous advisory is weak left, then we should either advise clear of conflict or continue to advise weak left. And again, these properties came from an analysis that I'm not going to go into. So again, this boils down to specific ranges on the inputs. And for this one, we actually found a counterexample. So by doing this algorithm, we actually found a place where we were able to satisfy all these constraints. And what that means is the network did not behave as expected. And so we could bring this back to the team that trained the network and say, hey, you've got a problem here. This is not behaving the way you expected. Maybe you want to retrain it or take other measures. So this is the kind of thing you can do. You can actually give strong guarantees in some cases, or you may be able to find places where the network doesn't behave as expected that may be very difficult to find with any other method. Okay, so just a word about some other ways you can use this technology. Of course, you've all seen this slide. The idea is there are networks where you have a known input and you perturb it slightly in a way that shouldn't affect the output, but it does affect the output, right? And so our tool can do some analysis here and help out. You can either prove for some given set of inputs that you are robust up to a certain level of perturbation. Or if you're not robust, again, it can give you specific examples where you're not robust. So I think the real advantage here of our tool is not so much in finding the adversarial examples, because there are a lot of other tools that can do that faster than running a mathematical proof engine, but in being able to prove that there are no adversarial examples, which other techniques can't really do. Okay, so just to tell you kind of where we are, we're working on a more detailed certification of these ACAS XU networks that we hope to actually be able to put on some planes and fly them in test planes. And then we're also looking at the main obstacle to really using this much more widely is scalability. So we could handle these networks with 300 nodes. We've improved this actually since I made these slides. Current techniques can maybe handle thousands of nodes. To really scale up beyond that is going to require a lot of interesting research, and we're working on that now. And then just sort of generally improving the robustness and expressive power of the tool, so you can look at other activation functions besides ReLU and other applications like autonomous driving. So that's what I have for you, and I'd be happy to take any questions.
So in how many sort of production quality neural network have you found prove the characteristic that they do not have adversarial, in the way with respect to slight perturbation? Have you found that? I can understand in some synthetic, or I just wanted to draw on your experience.
So generally, all networks have adversarial examples. So what you have to look at is maybe there are some regions where you don't expect any. And again, it depends on the application. Many applications, it's just there they are, and that's just life. But for this example, for this ACAS-XU, there are certain regions where you expect it to be uniform. And so we were able to prove that for some of those regions, it is uniform. And we were able to show some examples where it wasn't. But yeah, I think generally it's actually one of the things that this work demonstrates is that networks are not robust. And I think that's a big challenge. I'm not working on that challenge, but other people are. How do you train networks so they actually have this robustness property? And there's a lot of interesting work in that direction too.
Very intriguing talk. So if I'm understanding this, can your method be applied or are you trying to, in a way, also have a map of the decision boundary? And if the answer to that is yes, what are the advantages and disadvantages of this method compared to LIME or K-LIME methods?
Yeah, so you get kind of an implicit map of the decision boundary because the underlying tool has to, consider all those cases, but it's doing it symbolically. So you don't really get that explicitly. But another way to maybe think of this work is it gives you a toolbox for asking questions about networks. So you could ask questions like, where are the nodes that are very close to the decision boundary? And you might find some that you didn't know about or something like that. So it's really, I like to think of this as a general purpose toolbox for asking these kinds of general symbolic questions about a network. And I think there are a lot of applications we haven't looked at for that. I think you can use it to help with explainability, network simplification, looking at equivalence of networks, things like that.
Great, thanks. We have, was there one more question?
Here.
One last question.
Okay, so I'm curious to hear about the differences between robustness metrics for neural networks and your approach. In particular, I feel that sometimes those robustness metrics have a very deceiving name in that they are not really measuring the sensitivity of the network to adversarial samples based on a particular test sample. Mm-hmm. And I'm wondering how that compares to your approach.
Right. So our model is just to use some sort of norm, like an L-infinity norm. And I can readily admit that this is also an imperfect model. But the idea is we're going to cover everything in that ball. So you look at some ball around a specific input, and you're going to show that within that ball there's no adversaries. So it's not based on any kind of perturbation model. It's really looking at everything. You still could make the argument that, well, there might be some perturbations that are much more likely that are outside that ball than inside. And I think this is a fair question. But we're trying to solve this problem first, and it's already very difficult. So.
Thank you, Clark.